Welcome to lecture number 26 of fuzzy sets, logic and systems and applications. So, in this lecture we will discuss parameterized T norm. As we all know, parameterized T norm is also known as parameterized S conorms. So, in parameterized T norm operators, we have certain classes of T norms like Dombey's class of T norm, Debye-Sprade's class of T norm and Jaeger's class of T norm. So, let us first discuss Dombey's class of T norm. Here if we have two fuzzy sets A and B with the universe of discourse capital X. So, the Dombey's class of T norm is defined as T lambda of mu A of x and mu B of x. Here T lambda is for Dombey's class, and this lambda here is a parameter. So, this will appear in the right hand side. So, T lambda of mu A of x and mu B of x, and this is equal to 1 over 1 plus 1 over mu A of x minus 1 raised to power lambda plus 1 over mu B of x minus 1 raised to power lambda, and then whole raised to the power, as you can see here, 1 over lambda, where this lambda is in between 0 and infinite. So, the lambda values can take any value in between 0 and infinity. This mu A of x and mu B of x denote the membership function values for fuzzy sets A and B respectively, you can see here. So, it is very clear from this expression of Dombey's class of T norm that this T lambda applies to any two values of membership functions. So, this can be very well understood by this example here. So, if we take an example here where we have two fuzzy sets A and B. In this case, we have fuzzy sets A and B are discrete fuzzy sets. Then let us use Dombey's class of T norm for the intersection of A and B. Under the universe of discourse capital X, which is equal to 1 and 2. So, let us now find out these the Dombey's class of T norm for the intersection of A and B. So, you can see here that we have one fuzzy set here, which is a discrete fuzzy set as I mentioned, and this is represented by, you see here, by this figure, and similarly we have another fuzzy set B, which is you can see here represented by this figure. So, we have two discrete fuzzy sets A and B, and you see here these are defined by these two expressions. Now, let us apply the Dombey's class of T norm for finding the intersection of A and B. So, it is very simple. We will have to take the membership values of the fuzzy sets A and B respectively, and then we will apply the Dombey's class of T norm formula, and this way we get the result as you see here when we apply. So, we see that we get two terms as a result of Dombey's class of T norm for lambda is equal to 1, and when we simplify these two terms, we are going to get these two terms as the element of the resultant fuzzy set, which is nothing but the intersection of fuzzy set A and fuzzy set B based on the Dombey's class of T norm. So, this is coming out to be 0.096 over 1 plus 0.44 over 2. So, we have two elements of the resultant fuzzy set. So, we can say when we take the intersection of these two fuzzy set using the Dombey's class of T norm, we are going to get this thing, and you can see here this is plotted, and please understand here we have taken the value of the parameter lambda equal to 1. So, here we can change the value of lambda. Let us take some other values of lambda and see how the results vary. So, when we take lambda is equal to 2, we see that we are getting the intersection of A and B as a fuzzy set whose elements are 0.1 over 1 plus 0.49 over 2. So, this way here the intersection of fuzzy set A and fuzzy set B, obviously both the fuzzy sets A and B are the discrete fuzzy sets, and when we take the intersection of these two based on the Dombey's class of T norm, we get this as the output which has been plotted here. So, similarly, we can now increase the value of lambda further and see what is happening. So, we see that on applying the Dombey's class of T norm for lambda is equal to 3, we are getting here the elements of the resultant fuzzy set, and this resultant fuzzy set is the intersection of the fuzzy set A and fuzzy set B, which is giving us this the fuzzy set. So, here also when we plot the fuzzy set, because it is a discrete fuzzy set. So, we are getting the plots for the discrete points, and we see this as the result of the intersection of the two discrete fuzzy sets A and B. So, this way we have understood that the Dombey's class of T norm can be found by applying this expression T lambda of mu A of x and mu B of x, and this is equal to 1 over 1 plus 1 over mu A of x minus 1 raised to the power lambda plus 1 over mu B of x minus 1 raised to the power lambda, and then whole raised to the power 1 over lambda. And this way, by substituting lambda is equal to 3, we are getting the expression of the resultant fuzzy set. And please understand, this expression is applied for the membership values of the corresponding fuzzy set for which we are interested in taking the intersection. So, since this is a discrete fuzzy set, we first take all the elements and then we take corresponding membership values of the fuzzy set A and fuzzy set B, and then apply the T norm of the Dombey's class. So, if we look at all the results, we see here for lambda is equal to 1, lambda is equal to 2, lambda is equal to 3, we see that the membership values of the resultant fuzzy set increases as we increase the values of lambda. So, when we increase the value of lambda, the resultant membership value also increase. Now, let us go to Dubais-Pradet's class of T norm. So, if we take A and B fuzzy sets again, and with the universe of discourse x, The Du Bois-Pradès class of T norm is defined by this expression you can see here, and here we have another parameter, that is alpha. So, we write this Du Bois-Pradès class of T norm as T alpha, and alpha value can be from 0 to 1. So, Du Bois-Pradès class of T norm is defined by the T alpha of mu a of x and mu b of x, and this is going to be equal to mu a of x into mu b of x over max of mu a of x, mu b of x and alpha. So, this very simple expression here, and Du Bois-Pradès class of T norm is found by using this expression. Again, the Du Bois-Pradès class of T norm is used for taking the intersection of any two fuzzy sets. Here we have two fuzzy sets A and B, whose intersection is found by using Du Bois-Pradès class of T norm. So, when we use this formula, here we have, as I mentioned, T alpha. Alpha here is a parameter, and alpha, this parameter value can be any value from 0 up to 1, as I mentioned. And when we apply this, we get the resultant membership value, or I would say the membership value of the fuzzy set, which is the intersection of fuzzy set A and fuzzy set B. So, this can also be understood by an example here. So, we have two discrete fuzzy sets, fuzzy set A, fuzzy set B. Here you can see. So, fuzzy set A is equal to 0.7 by 1 plus 0.5 over 2, and then B fuzzy set we have 0.1 over 1 plus 0.8 over 2. So, these two fuzzy set we have, and we are here interested in finding out the intersection of these two fuzzy sets for different values of alpha, and these values of alpha are 0.1, 0.2, 0.3, and this is again through the intersection is found through the Du Bois-Pradès class of T norm. So, if we take two fuzzy sets as shown here in these two plots, these two fuzzy sets are the discrete fuzzy sets A and fuzzy set B. So, A is this fuzzy set and B is this fuzzy set, and when we use the formula that I have already discussed just now, the formula here is T alpha of mu A of x and mu B of x. This is giving us the mu A x into mu B x over max of mu A x, mu B x and alpha. So, let us now take alpha is equal to 0.1 and see what is the membership value of the corresponding resultant fuzzy set, and this again this resultant fuzzy set is the intersection of fuzzy set A and fuzzy set B. So, when we apply this, we find here the resultant fuzzy set, which is the intersection of fuzzy set A and fuzzy set B, and this resultant fuzzy set has two elements. So, we have here 0.1 by 1 plus 0.5 by 2 as two elements of the resultant fuzzy set. So, when we plot this, the fuzzy set looks like this. So, here I can write that we are taking the intersection of fuzzy set A and fuzzy set B, and this is giving us the resultant fuzzy set here, and this fuzzy set has again two elements, and this looks like as it is shown here in this slide. As a result, now when we take some other value of alpha, so here we are now increasing the value of alpha. In earlier example we have alpha is equal to 0.1, in this example we have alpha is equal to 0.2. And let us see what is happening, how the result is varying, how the elements are changing. I mean these elements are from the intersection of fuzzy set A and fuzzy set B. So, again I can write here that this is the intersection of fuzzy set A and fuzzy set B, and here we are getting the resultant fuzzy set, which again is having two elements as 0.1 by 1 plus 0.5 by 2, and when it is plotted it looks like as it is shown here. Now, again we change the value of alpha, and we increase the value of alpha here. Now, for alpha is equal to 0.3, when we substitute in the expression that is given for Dubais-Pradès class of T norm, we see that the resultant fuzzy set again has two terms, two elements, and these elements are 0.1 by 1 plus 0.5 by 2. So, when we take intersection based on the Dubais-Pradès class of T norm, we are getting here the resultant fuzzy set, which is shown here like this. So, what we have done in this Dubais-Pradès class of T norm, we applied Dubais-Pradès class of T norm for taking the intersection of fuzzy set A and fuzzy set B, and then the resultant fuzzy set we have obtained based on the Dubais class of T norm. And we see that when we increase the value of alpha, like in the first case we took alpha is equal to 0.1, the second case we took alpha is equal to 0.2, and then we took alpha is equal to 0.3, and we see that the values of the membership, we can see here the values of the membership. So, let us now quickly go to the first case where we took alpha is equal to 0.1. So, you see here 0.1, and then when we change the value of alpha to 0.2, we see that there is no change in the output, there is no change in the membership value even when we change the value of alpha. So, this way we see that for the values of alpha, here the change is not very significant in the values of alpha. So, because of that the membership value of the resultant fuzzy set is also not changing significantly. Now, let us talk about the Jaeger's class of T norm, which is the another class. So, in Jaeger's class we see that if we have two fuzzy sets A and B, and within the universe of discourse capital X. So, Jaeger's class is defined by the expression which is given here. The Jaeger's class operator is represented by T subscript W. So, T W is operated on a pair of membership values. Here we have these pairs as mu A of x and mu B of x. So, we can say that T W of mu A x and mu B x here, and this is equal to 1 minus min of 1 and 1 minus mu A of x raised to the power w plus 1 minus mu B x raised to the power w, and then whole raised to the power 1 over w, you can see here. So, we take min of this and this, and here the value of w lies in between 0 and infinity. So, when we are interested in finding the intersection by using the Jaeger's class of T norm. So, let us see how it works. We have this example here where we have taken two discrete fuzzy sets A and B, the same fuzzy sets, same discrete fuzzy sets as we have taken in the previous example. So, here when we apply the Jaeger's class of T norm on these two fuzzy sets A and B, when we apply the expression for the Jaeger's class of T norm on the membership values of fuzzy set A and B. So, we get this expression finally. You can see all these steps are shown very nicely for understanding. So, we get again two terms where we have taken W is equal to 1, and for W is equal to 1, when we apply the Jaeger's class of T norm for finding the intersection of fuzzy set A and fuzzy set B, we are getting here two elements. In fact, we are getting only one element, because the two elements that are mentioned here, one has the 0 membership value. So, 0 membership value is normally not included when we represent a fuzzy set. So, you see that when we take the Jaeger's class of T norm, we get the resultant fuzzy set whose elements are 0 by 1 plus 0.3 by 2. So, this way as I already mentioned that one of these elements has 0 membership value. So, it is shown here, but it need not be included while writing the discrete fuzzy set of the resultant of fuzzy set and fuzzy set B. So, it is shown here, the resultant fuzzy set is shown here, which you can see at x is equal to 1, this is x is equal to 1, we have 0 membership value, and at x is equal to 2 as the generic variable we have membership value 0.3. So, you can see here we have 0.3. So, this way we can find the intersection of any two fuzzy sets based on the Jaeger's class of T norm for W is equal to 1. Now, for the same set of fuzzy sets, we find the intersection based on the Jaeger's class of T norm for W is equal to 2. So, when we increase the value of W here to 2, we see what is happening. You see that on applying the Jaeger's class of T norm expression, we are getting here two elements of the resultant fuzzy set, which is coming because of the intersection here of the fuzzy set A and fuzzy set B, you can see here. So, this way these two elements, if we see, we find in the previous case where we had W is equal to 1, this term had the membership value 0, whereas here we see the membership value is not 0. So, membership value for the first term here is 0.051 for x is equal to 1, and the other term has the membership value as 0.46 at x is equal to 2. So, you see here both the terms have been written here, and this is the resultant of the intersection of fuzzy set A and fuzzy set B. So, we can clearly see that by increasing the value of W, we see that the membership values are also increasing. Now, let us take the value of W 3 and see that this value is the membership value of the resultant fuzzy set is again increased. So, this way we see that when we increase the value of W, the membership values of the resultant of the intersection based on the Jaeger's class of T norm also increases. So, now let us compare this. So, I would just like to repeat what I have said again. here. So, we see that while we took the Dombey's class of T norm, we see that in Dombey's class of T norm we have lambda, and you see here this is for lambda is equal to 1, and when we increase the value of lambda here to 2, so we see that the membership values of the corresponding terms of the resulting fuzzy set out of the intersection of fuzzy set A and fuzzy set B increase. Similarly, here lambda is equal to 3, we have once again we see there is increase in the membership values. Similarly, when we talk of Dubais-Pradès class of T norm, with the increase of the alpha as the parameter, if we increase here, since the change is not very significant in alpha, so the significant change is also not seen. So, in the you see the membership values of the resulting fuzzy set out of the intersection of fuzzy set A and B. So, we do not see any significant change here for alpha is equal to 0.1, 0.2, 0.3, and when we see the Jager's class of T norm, we see that when we increase the value of W, we see the change in the membership values of the resulting fuzzy set, which is out of the intersection of fuzzy set A and fuzzy set B. We can see here this is for W is equal to 1, and this is for W is equal to 2, and here we have W is equal to 3, and we can see that the membership values for the corresponding generic variable values are increasing. So, this way we see that we have covered the parameterized T norms, and in the next lecture we will discuss the parameterized S norms or T conorms. Thank you.